Here we go. Hey, everybody. What is going on? Welcome to this tutorial as part of Transform 2022. We've got the PyLops crew here. So looking forward to a good tutorial from them. Transform, as you probably all know, is a virtual festival of digital geoscience, all free and open access. So right off the start, really want to thank curvenote.com for their support of Transform. If you haven't checked out CurveNote, you should. Really great way to do scientific computational notebooks and writing. If you're writing papers or doing notebooks and you want to version them and get them online, really slick way of doing that. So check that out. You can find the full schedule for Transform online at softwareunderground.org/transform. And you can join in the Slack conversation there. There's links to all of that. Remember, at any time, you can pause and rewind the video. Please feel free to share it, like it, and subscribe to the channel. All right, so without further ado, we're going to learn all about PyLops here and take an interesting approach to looking at how to use it to solve a geophysics problem in a number of different ways. So I want to welcome Carlos de Costa, Nick Luiken, and Matteo Ravasi, and we'll look forward to hearing from them.
All right. Well, thanks a lot, Brandon. Thanks a lot for the introduction, and everyone in the Software Underground for keeping up with this type of events. Hopefully one day we are back live, but this live stream is quite good because allows me to be 8 p.m. in the office and Carlos probably 6 a.m. in the office, but you guys get a full experience all the way from Saudi Arabia to Canada. We have been doing PyLops tutorials for a few times now at Transform. So today we decided to take a slightly different approach. That was actually inspired by a suggestion from Matt. We will take a problem and we'll try to see how PyLops alongside other libraries in the Python ecosystem can help us solve this problem. You'll see in a minute which problem we decided to take. And later, Carlos will present our initial attempt or some of our work in progress into making PyLops v2, which will improve upon some of the initial, perhaps not so good design and provide you with a lot of new features. So just to start, we have everything on the GitHub repository that you can see here, was already shared. You can just clone it or download it. We give two options as usual. If you are familiar with setting up your own Python environment, feel free to do it and use our environment YML file to be sure you install all the libraries. Otherwise, mostly everything that you will see today, apart from probably a few small things in the second tutorial, can also be run on Binder. Just click this link. And if you want, you can run them also in Colab. And in that case, even some of the few things that Carlos will show and require access to a GPU, in that case, you'll be able to use them. So without any further ado, I'll just move to Nick, which will start and do the first half of the first tutorial and reveal what's the problem we have decided to take for you. So I'm going to stop sharing.
Then I will start sharing.
And that's it. We can see it.
Hold on, let me share my video. There we go. All right. Thank you for the introduction, Matteo. Thank you for inviting us to give a tutorial here. And thanks to everybody online attending. So the problem we will be discussing today is seismic deconvolution or spiky decon. And I'm actually quite happy that I get to present it today because it's probably the only time that Matteo will allow me to talk about it. It's a very nice problem. It's a very well-studied problem, and there's a lot of interesting components about it. So yeah, I think it will be a very nice tutorial. So Matteo already shared with you the links to the GitHub page and how you guys can access it. Yeah, so let me start by introducing the problem and discuss the theory in a nutshell. So there we go. So like I said, in this tutorial, we will talk about obtaining a reflectivity from some measured data where the reflectivity has been convolved with a
Nick,
with a
did you
wavelet.
move your screen down?
Yes.
We don't see it, or I don't see it. What about you come to my office?
Yeah.
Now we have a solution.
Let's try
B.
that. Yeah. Okay. Sorry about this, guys.
Let's, try this.
Should I do that? You sharing now?
Yes. Can you guys see? Can everyone see this?
Yep, I can see it.
You can see moving.
Okay.
Yeah, I think you guys are okay now.
All
That
right.
looks
Sorry
better to
about
me
that.
as well.
Apparently, the screen was not moving. So yeah, the problem we are going to discuss is to obtain reflectivity that has been convolved with a wavelet from certain measured data. And it can simply be written as follows. We have some data here that is described as the convolution of a wavelet that we see here in red with some reflectivity model here. And today we choose a rather simply reflectivity model with just 3 spikes. And then we obtain some data. And of course, we assume that we have some noise there. And our goal is going to be to, given this data here in blue, to retrieve the subsurface model represented by these 3 spikes. And we are going to discuss a bunch of different ways in which you can solve this problem. So we have here 6 different ways. Matteo is going to be talking about the last 3, and I will discuss the first 3. So we will start with doing a frequency domain deconvolution. That is, I think, kind of an industry standard that has a lot of history. And after that, we will move on to doing time domain deconvolution via least squares inversion. And this is kind of the first part where we really start to leverage the PyLops toolbox. And yeah, we will show how it can help you solve this problem. And after that, we will move from a rather simple least squares solution to a sparse inversion that requires some more complicated solvers. And here we will use the kind of the sister toolbox of PyLops called PyProximal, where all these algorithms are stored for you. And then Matteo is going to talk about solving this problem from like a deep learning angle. So he will talk about doing automatic differentiation, something called deep image prior. That's kind of a preconditioner that helps you solve inverse problems. And lastly, he will discuss doing like a fully data-driven deconvolution, where we basically throw out all the physics and don't do any modeling at all. And all of this can be done very nicely with PyLops, and that's what we will show you today. So here, if you need these libraries here, you can run this cell. I will import all the libraries that I need. Run this, set the seed, and then we can start creating our data. So let's go through the cell. Here we choose a number of time samples and a time sampling. And our F0 here is the peak frequency of the Richter wavelet that we are using. So now we simply set up the time axis here, and we set up a spatial axis where at these 3 points here, we impose a spike. So that will be a reflectivity. And then what we can do is we can get H, which is our Richter wavelet, the center of the Richter wavelet, and the axis of the wavelet from the PyLops toolbox. So we simply use PyLops, utils wavelets, and the Richter wavelet we put in our time axis and our peak frequency, and that gives us all that we need. And then we will pass it on to this function called convolve1d. And what this does is this gives us a linear operator that will do all the matrix vector multiplications that we need without explicitly storing the matrix. Now, one very important thing when you implement linear operators is that you check that your forward and your adjoint match. So here we do what is called the dot test, and the dot test, it checks for us whether the forward and the adjoint are correctly implemented. And now here in the next section, we create our data. So Y is our data, C-op is the convolution operator, and X we have just defined as our reflectivity. And note that here we have overwritten the multiplication operator from Python. So when we use PyLops, we can simply use multiplication and it will do matrix vector multiplication for us. So this will be our clean data. And then we add to this data some noise and we call it yn. So from now on, Y is going to be the clean data, Yn is going to be the noisy data. And now we can plot what we have. So here, the first thing I've plotted is the convolutional operator. So this is the C-op that we are working with. And as you can see, it is a convolutional operator. It's actually a linear operator. And it has passed the dot test. So these two expressions should be the same. And as you can see, they are the same. And here we have in black our reflectivity. In red, we have the reflectivity convolved with the wavelet. So that will be our clean data. And in green, we see our noisy data. And as stated before, now we want to solve this inverse problem and obtain the reflectivity from ideally the noisy data and hopefully what we will start, of course, with the clean data first. So as I've stated in the beginning, we can actually solve this problem in the frequency domain. And the reason that we can do it is because there's this very nice relation between convolutions in the time domain and multiplication in the frequency domain. So when we do a convolution in the time domain, it's just multiplying the Fourier transformed coefficients. So here, for the components in the frequency domain, I will write the hat, and omega will be the frequency. So now, before we had a convolution here, but now it's just a multiplication. So D is going to be the pointwise multiplication of the vectors W hat and R hat. So first, we apply this Fourier transform. We obtain the data, the wavelet, and the reflectivity. And to obtain the reflectivity, we can simply do a pointwise division of the data and the wavelet. Now, the point is, or the issue is that this wavelet will be band limited, so certain frequencies will not be present. And as you can see, that means that we will basically divide by 0 here. So to prevent that, we have to introduce a frequency filter. And we denote that by phi, parameterized by lambda. So this lambda will be some water level that will prevent us from dividing by 0. And I've outlined here 3 popular approaches. Of course, you can come up with more exotic ones, but I think these are the three simplest ones that you come up with. So the first one, simply, when you divide by 0, adds some water level. The second one is a bit more complicated. It's a Wiener filter. So there you will divide the adjoint by x squared plus some water level. Or what we could alternatively do is simply cut off all the frequencies that we won't be needing. And now I will give 2 examples. One where I will use this frequency filter, and the second one where I will use this frequency filter. So let's look at how we can solve this problem here using PyLops. So the first thing I need to do is convert everything into the frequency domain, and that's what I do here by using the Fourier transform. And then we simply do a division. So here we have our reconstructed X, which is the Fourier data divided by the data of the Ricker wavelet. And here you see a small water level. So when we do it for the noisy data, of course, to compensate also for the noise, we need a little bit higher water level. And then to obtain everything in the time domain, we simply have to do an inverse Fourier transform. And let's see what we get. Right, so I will zoom out a little bit so you can see the 4 figures. Yes. So here at the top, we see the spectrum of our wavelet. And as you can clearly see, it is lacking a little bit in the low frequencies, but mostly in the high frequencies. Let's start from saying like 60 hertz. Everything is pretty much 0. And we can clearly see that when we reconstruct the reflectivity, that all the information that we should be having in the higher frequencies is completely gone. So here in the lower frequencies, we seem to be matching the spectrum of the reflectivity quite well. But in the high frequencies, we have a lot of issues. And we see that the problem is basically in our data, because the reflectivity does contain the high frequencies, but in our data, it is not present. So we can never hope to retrieve any of the information from the reflectivity in this area. And then when we do our reconstruction here at the bottom, we see the reflectivity in black. In green, we see the reflectivity that we obtain from the clean data, and the red one is from the noisy data. Now, as we can clearly see, structurally speaking, the green one seems to be doing relatively well. It at least knows the location of the spikes, but the problem is that it cannot really reconstruct the spiky profile, so it's very smooth. And we see that in red, we see basically a very noisy reconstruction. So now, let's go down and try it with a different filter. Right. So here we have our wavelet. And again, we see here our reflectivity. And now what I've done is I've chosen a different filter. So what you can see is that we are actually able to resolve the higher frequencies component a little bit better. And especially here in the part where we do have information, it's already a lot better. Still, though, there is information lacking from the high frequencies, so we cannot really reconstruct the spiky profile. But when we look here, we see that we do, I would say, a little bit better. So here in green, we now have the reconstruction from the clean data. So you see it's really trying to get this spike, but it's struggling because it misses a lot of information. And in red, we see this kind of over-smoothed reconstruction from the noisy data. So this is from when we solve this problem in the frequency domain, it's pretty much the best thing we can do. So let's now move on to the time domain and see how things are there. So we'll zoom in again a little bit so you can read the screen a little bit better. So what we do in the time domain is we basically write the convolution as a matrix vector multiplication. So we have our data here. We have a matrix W that describes a convolutional operator. Again, R is a reflectivity, and N is some noise that we introduce into the inverse problem. Now, what PyLops is going to do for us is basically going to model this matrix vector multiplication with the operator W. And of course, to solve this problem in the time domain, one of the simplest things to do is to do a simple least squares inversion. So there, instead of solving a linear system directly, we solve the least squares problem. So we try to minimize the distance in an L2 norm sense. And that corresponds to doing a maximum likelihood estimator where you assume white Gaussian noise. Now, you could choose different data norms, but then things become a little bit more complicated. And anyway, in our examples, we add some white Gaussian noise. So for this particular example, it's appropriate. Now, because we have noise in the data, and because, again, we have this problem of missing frequencies which makes the operator W ill-posed, we have to add some regularization. So here we start by simply adding some Tikhonov regularization, which is a quadratic penalty of this form, and that basically prevents the reflectivity from blowing up. And the blow up is something that you would get by doing the inversion and amplifying noisy components. And because both our data term here and our regularization term are smooth, we can simply compute gradients. And for this example, we put it to 0. And then we obtain an expression for our reflectivity as parametrized by this parameter lambda. So this is now what our solution looks like and how we could compute it if the problem was, of course, small enough. So let's see how we do that in PyLops. So here's a callback function that will compute the errors for us. And here we make 2 lists that will compute these errors. And here we see our first function called LSQR PyLops. So this is PyLops. That's the LSQR function that's within PyLops that allows you to pass the linear operators that we need. I assume everybody's familiar with LSQR. We put in our linear operator. We put, in this case, in our clean data. And here are some parameters that LSQR needs. So, for example, the maximum number of iterations. And then we pass the callback function so we can compute the error with the true solution. Now, we do the same with the noisy data here. And then let's see what we get. Right. So here, again, in black, we see the reflectivity. In green, we see the reconstruction from the clean data, and in red, we see the reconstruction from the noisy data. Now, the attentive listeners may see that this solution actually looks a lot like the solution that we got here in the frequency domain by applying this Wiener filter. And this is no coincidence, because as you may expect already, because we can do a Fourier transform and pass to the frequency domain, the solutions in the time domain and in the frequency domain for certain regularization terms are actually equivalent. So if we now assume that we have periodic boundary conditions for the convolution, then our convolutional operator W is what is called a circulant matrix. I will later show what the structure of that matrix is. And a property of these matrices is that they diagonalize under the Fourier transform. So that means that when we write the Fourier transform as a matrix F, and we do FW F transpose, we will end up with a diagonal matrix that will contain the Fourier domain elements of W. So that's basically the spectrum of the wavelet. But this is also our eigenvalue decomposition. And here we plot the full matrix W. So this is a nice feature that PyLops allows you to do. So here we have the Fourier transform operator, and we have our H operator that does the matrix multiplication with the circulant matrices. And the add symbol, it does the multiplication for us. And when we do 2 dense, we actually get the full matrix so that we can plot it, for example. So here we see what is called the circulant matrix that does the convolution for us. And here in the middle, we see the spectrum. So these are both the Fourier coefficients and the eigenvalues of the matrix W. Now we recall that by doing Tikhonov regularization, we obtain a solution of this form, and then plugging in the expression that we got before for W, we see that we end up with a reconstruction that looks like this in the Fourier domain. So we have Fourier matrix here. Then we have our Fourier elements, lambda H lambda, some water level here. We invert, so we basically do a division. And then again, we have our Fourier coefficients here, and FD are the frequency components of our data. So you can see that this is actually equivalent to applying a filter to the spectrum of this form. And this is precisely the Wiener filter that we saw before. Now, equivalently for the first example, where we use this filter, that will correspond to solving this problem in the time domain, and that is known as Lavrentiev regularization. And finally, if we apply the filter where we just simply truncate the frequencies, that will correspond to solving this linear system by doing what is called a truncated singular value decomposition. All right. But up until now, we have done something in the frequency domain. We have solved the problem in the time domain. But the results were not that satisfying. And due to the lack of high frequencies, we were really unable to get very clean, spiky reflectivity. And the way to obtain spikiness in our solution is by leveraging what is called sparse solvers. So instead of what we do in the Tikhonov regularization, where we add an L2 penalty here, we add a penalty with a different norm. So here we write the P norm, and generally speaking, if you want to do a sparse inversion, you have to choose P smaller than 1. And by far the two most popular options are choosing P is 0, which is the L0 pseudo norm that simply counts the number of non-zero components in your solution, or you choose P is 1, which is the L1 norm, and that's the one that is most commonly used because your objective function will still be convex. Now, one issue that we start having now is that, theoretically speaking, the objective function is no longer differentiable. And that is an issue because if we want to use gradient-based solvers, we can no longer do it. And therefore, we have to use more specialized solvers. So for these problems, one that is very popular is called orthogonal matching pursuit. And that basically solves this problem when P is 0. And two other extremely popular algorithms are the iterative shrinkage thresholding algorithm, ISTA, and its faster variant, FISTA. And they solve this problem when P is 1. And these solvers are embedded into PyLops. As you can see, they are in the optimization section, specifically under sparsity. And they work very similar or we can call the functions very similar to the way we called LSQR before. So we just get the solvers from PyLops. We pass the linear operator, we pass the data and the number of iterations that we want to do. And then we just let it run. And now here we see the solutions that we get. So as you can see, all of the solvers are able to retrieve the spikes that we are after. This is, I think, yes, this is the result for the noiseless data. So indeed, the results look very clean. And as you can see here, O and P converges very fast. And ISTA and FISTA need a little bit longer, although they solve up to, I think, a high accuracy quite fast also already. The reason that O and P is very fast in this case is because it's a greedy algorithm. So it will basically start from a 0 solution and then start adding components. Now, you can imagine if you have only 3 components in your solution, then, of course, it will converge very fast. However, when we start moving to very large-scale problems, then OMP is not competitive at all compared to ISTA or FISTA. So we will focus mostly on ISTA and FISTA because we have large-scale applications in mind. Now we can do the same trick with the noisy inversion. Still, we obtain spiky solutions, but you see that they are degraded a little bit due to the noise that is present in the data. And here again, we plot the residual norms. All right. So up until now, ISTA and FISTA have been kind of a black box algorithm, but they are part of a class that are called proximal algorithms. And these proximal algorithms, they are used for algorithms for solving objective functions of the form f plus g. So we have a sum of 2 terms. F will generally denote our data term, and in most cases, this will be smooth. And then we add some regularization to constrain our solution, and that is generally speaking non-smooth, but still convex. So norms we are thinking about here are generally speaking, I think L1 norms, and TV, for example, total variation also falls under this class that can be solved using proximal algorithms. And to solve these problems, we have to resort to iterative-based solvers. So for the Tikhonov regularization, we could write out an explicit solution, but here that is no longer possible. So what we do is we take a gradient step that we see here over the smooth part, so over the data term, and after that we apply what is called the proximal operator of G to the result. And we keep doing that in an iterative fashion. Now, to explain in detail what these proximal solvers are is, I think, a bit outside of the scope of this talk. But we have a lot of tutorials in the sister toolbox PyProximal, where you can learn a lot more about this. And basically, all of your favorite solvers for non-smooth optimization are there. So things like ISTA, FISTA, Primal Dual, everything is in there. So we encourage you to have a look. And the way that we can set up these algorithms, it's really quite nice. So as you can see from above here, we need to have the proximal operator of a certain function G. And for a large class of functions, this proximal operator has a closed form solution, and they have all been embedded into the PyProximal toolbox, so you don't have to compute them yourselves. It's already been done for you. And if you want to do, for example, spiky decon, where we have an L1 regularization, then we simply call L1 from the PyProximal, and it will compute the proximal operator of L1 for us. Now, for L2, this will simply be this gradient step that we see here at the top. And here we pass our linear operator and our data term, Y. Now, here are some technicalities. We need to choose an appropriate step size that is going to be the Lipschitz constant, so the largest eigenvalue of the Hessian of our problem. And we have to choose a regularization parameter. So here, we simply call from PyProximal the proximal gradient algorithm, which is ISTA, and its faster version, accelerated proximal gradient, which is FISTA. Then we pass both our functions that we defined here above, so L2 and L1. We pass the step size, the number of iterations, and we let PyProximal do the magic. It ran already. And here we see the result. So one thing I want to stress is, okay, of course we can do this for L1 regularized problems, but PyProximal really has a large class of proximal operators in there, and it allows you to do to work with many regularizations. So we can do, for example, isotropic TV. We can do anisotropic TV. We can do low rank optimization. Yeah, and if anything is missing, please reach out to us, and we see if we can embed it in there. And yeah, so like I said, we can very nicely solve for this spiky reflectivity. Now, there is an algorithm that recently came to our attention that we did a little bit of work on, and it's called accelerated FISTA. So this is an even faster FISTA. And that algorithm basically introduces a weighted norm. So we see a matrix D here, and that is a diagonal matrix, which is 1 over the absolute value of our reflectivity. And this, you can show, actually approximates the L0 pseudo-norm. So it is generally believed that these L0 problems give you a higher level of sparsity. However, because you no longer have a convex objective, this is not favorable for large-scale problems, so we do have a little bit of a trade-off there. But a FISTA shows that you have this, you still have a an objective function you can solve with these proximal algorithms, but it is a bit sparser than Vista itself. Now, of course, we don't know the reflectivity beforehand. So what we do is we get our estimate at every step, RK, and we simply do approximate the matrix D by dk, which is 1 over the absolute value of RK, our current estimate. So now we have somewhat of an IRLS type algorithm to solve L1 regularized problems. Now let's see A-Vista in action as well. So clearly here we can already see from this figure that A-Vista is even a little bit better than Vista in retrieving the spiky structure. It goes up, it corrects for the amplitude a little bit better. And now here what we do in our last example is we show the error as a number, as a function of the number of iterations. So here we see all of the solvers that we have used before, the least squares, which is of course not able to get the spiky structure, so the error remains quite high. ISTA is able to get the spiky structure, but it's a little bit slow. Vista, as you can see, is much faster, but it stagnates at some point. And here, A-Vista is even able to get higher accuracy than Vista, and that is even more pronounced when we look at the error norm for the noisy data. So A-Vista really does a great job here. So this concludes my part of the talk. I hope you all enjoyed it. And I will now pass on to Matteo, who is going to be talking about using deep learning and also leveraging the PyLops toolbox with that. And he will show how we can solve the spiky deconvolution problem that way. So I'll give the floor to Matteo.
All right. Thanks a lot, Nick. Great start of the tutorial, at least for me. I hope for you guys too. So what we're going to do in this second part, I want to start with a disclaimer. We're not here to argue that the best way to solve this problem is using deep learning. Perhaps at the end you will see that that's our conclusion. But what I want to show is how deep learning and some of the learnings that we are getting from that community can still be very valuable, very useful for geophysical problems, and for some geophysical problems that maybe are more suitable than simple spiky deconvolution. And along the way, show how we can embed the PyLops together with PyTorch, allowing us not to start from scratch, re-implementing our physical operators, which for convolution could probably take a matter of a few minutes, maybe half an hour. But if you want to now re-implement the entire PyLops library in PyTorch, which was an initial attempt of mine that I immediately realized was not a good idea, I'll show you how you don't need to do that. And even if you are using GPUs, there is a very nice set of libraries that we leverage under the hood, and they allow you to directly interact or allow your vectors in PyLops, which are generally NumPy and CuPy vectors, and your vectors in Torch, which are generally Torch tensors, to interact with each other without really never doing any movement, physical movement in your memory. So never moving back and forth from the GPU and the CPU, or never moving from one part of the GPU to another part, because these libraries need different areas to store information. So all of this is not done by PyLops. It's done by a bunch of fancy libraries that we use under the hood, but we allow that so that you should not be afraid of using PyLops with the CuPy enable together with PyTorch. You'll get the exact same performance as if you were to re-implement it in PyTorch yourself. Okay, so the very first example that I want to show is, what about Autograd? I hear from my young students that computing gradients yourself is old-fashioned and outdated. Just compute the forward, give it to PyTorch or TensorFlow. They'll make the gradient for you. And I always say, yes, but they're not magic. They're doing the gradient for you under the hood the same way we are doing it in PyLops. So you'll see a function somewhere that if you're doing a convolution is implementing a correlation and is calling it backward. But when you use automatic differentiation, you need to be careful that there are some problems, as we will see in a minute, that they need some care, because the automatic differentiation will give you the gradient, so that will be perfect. But the moment you pass it to a solver, you need to know exactly whether that solver is suitable for your problem. Not every problem can be solved with Adam. I'm sorry to open a Pandora box here. Okay, so how do we do it, and what do we do? The very first attempt, we're just going to solve the exact same problem we solved before, so a L2 inversion, but instead of using PyTorch and PyLops and LSQR, we're going to use PyTorch and a standard gradient descent. The very first line of code, if there is anything you have to remember from the second part of today's talk, is this line of code. This line of code is very important. It currently belongs to the sister library PyLops GPU. Is likely to be finally integrated straight into PyLops, so you would not need to install PyLops GPU just for mostly for this class. But what it really does, it takes a PyLops operator. It could also take a native PyLops GPU operator, but we kind of stopped developing that library for the reason I mentioned before. So it takes a PyLops operator that could be both running on a GPU or on a CPU, and it just wraps it up into a torch module, basically making torch aware that anytime this goes in your computational graph, when you want to do the forward pass, it will apply the forward of the operator. And instead, when you want to do the backward pass, what in PyTorch is called the backward pass, or the pass of back propagation, you will call the adjoint of the operator, because if you are good with math, you will realize that the backward or the gradient of a linear operator is times a vector is the adjoint times the vector in the other space. So this is basically the main trick that we do, and this allows us not to have to implement any of the operators in PyLops while still being able to mix and match them with the native PyTorch operations. Second thing that we do, of course, everything has to now become a torch tensor. Our model vector, our data, they need to become torch tensor. So we just moved our data to a tensor, torch tensor, using torch from NumPy. And we also say that we're going to start from a generic starting model. In this case, will be a vector of zeros. And we say that the problem we want to solve, as you have seen before with Nick, requires you to optimize for this reflectivity, this vector x, while running, for example, your gradient descent. So how do you do this in Torch? You simply take a Torch tensor and you ask Torch to be able to compute the gradient every time you ask for it. So in general, if you do deep learning, as we will do towards the end with a classical sort of neural network type of approach, what you want Torch to apply the gradient to are the weights and the biases of your network. But here we are just using Torch, I would say, in a slightly different way from what 99% of the people use, but it's totally fair that you can use Torch as a classical library for optimization using automatic differentiation. This is not out of scope of Torch. It's just not what Torch became famous for, or popular for. So after this, we have to define an optimizer, which in a way is slightly similar to what we do in PyLops, but in this case, we decide to use gradient descent. Again, for reasons that will become clear maybe later, you don't have gradient descent in Torch. You have a stochastic gradient descent. But if you run stochastic gradient descent and you pass your entire data set, then you are running a classical full gradient descent. You pass the parameters that you want the optimizer to optimize. So in this case, the vector x. And then you pass the learning rate, or if you are more into an optimization type of skill set, you will call this the step size. And we also add the momentum, which is a well-known trick to make these solvers converge faster. We also show that you can have a scheduler, as classically done in optimization and as well in deep learning, that reduces this step size along the iteration. So we're just using this reduce on plateau to show that you can use many. But in the next example, it will become very clear that we want to use a specific one to get good results. Okay, so after this, this part, if you have ever trained a neural network in Torch, will be quite familiar to you. In Torch, you generally do not have very high level optimizers that do everything for you, Kera style. You could do it if you use PyTorch Lightning, but we are not here. So you just do a loop yourself along the amount of iterations you want to solve your problem for. You take your optimizer and make sure the gradient is set to 0. Then you do the forward pass. Then in this case, we'll just be applying the convolution operator to this vector x that we want to solve for. Then you compute your loss, which again, in this case, is a simple L2 square. So you square the difference of these two vectors, the true and the one we predicted, and then you compute the mean or the sum that won't change. You then compute the backward, and this will give you the gradients, and you ask the optimizer to move a step. If you have a learning rate to adapt, you also ask to adapt it. You'll see that we need to run this for quite a lot of iterations. Will become clear in a minute why, but you see that the residual is reducing very fast. So before I make this plot, you will be quite tempted to say, we're going to get a very nice result. All right, let's see. The result that we get is actually very poor. So why is it poor? I mean, automatic differentiation is perfect. It's giving us the gradient with no reason to doubt the gradient is correct. And we are using gradient descent. That should converge. And in fact, if you look at the bottom plot, this is the data, the true data, and then the green is the predicted data from the predicted model. So we are matching the data perfectly. Well, this goes back to what Nick discussed. It doesn't matter whether you use Torch or PyLops, or whether you implement yourself gradient descent or you use the one of PyTorch. The problem that you are missing the high frequencies will still be there. So how do we improve this? Well, we already sort of explained how you improve this. You add prior information in the form of L1 regularization. But as Nick was stressing before, the L1 norm is a non-differentiable norm. At least is non-differentiable at 0, because at 0 you have many possible derivatives, or at least you have one derivative you come from the left, one if you come from the right. So if you ask to someone that is a pure optimizer, he will tell you that you can never use gradient descent for this type of cost functions, because what you are actually using is something called subgradient descent that is known to be the slowest possible iterative solver that you can generate or create. So if we are using now a gradient descent from Torch, if you're not very careful about what we are really doing, we are solving the problem with a subgradient descent, which by far will be slower than sort of the best in class we have seen, the Fista or A-Fista. But what we want to show here is that if you're careful in the way you do it, you can actually get a good solution. And what careful means, it just means that compared to the block that we had above, you change the scheduler by making sure that your learning rate or step size decreases slowly through iteration. So when you get closer to the solution where you are very close to having some reflectivity is equal 0, so close to the non-differentiable part of your regularizer, you are a bit gentler in how you step from one iteration to the next. And of course, in this case, I must say Torch is very nice because you can simply just make your data term as before. Now you can just make a regularization term that is nothing more than the sum of the absolute of the solution. You just patch them together and you compute the backward. And in this case, Torch will know everything through the computational graph and will give you now the gradient of this loss, not just the data term. So let's run this and let's see what happens. You can see that this is going to take a bit longer than solving, for example, the problem with Fista. And this is not surprising because instead of using a highly specialized solver for the problem at hand, we are just trying to use the most sort of off-the-shelf solver that can solve any problem. And of course, if you can solve any problem, you're unlikely to be the best in class for all of them. We could also probably stop it earlier. We're just letting it run for a lot of epochs just to make sure we get to a good solution. And this is the result we get. So you can see the residual is almost down to 0 very fast. But I mentioned before, it was also almost down to 0 in the previous problem, but the solution was bad. So seeing the residual going down to 0 is not a sign that we are getting a good solution. And in fact, in this problem, the red curve will be going down to 10 to the minus 3, while in the previous problem, it was going down to 10 to the minus 4. And this is because now we add the prior information, and the solver has to trade off between the two sort of requests we are making for it. But now you see the solution is much better, very similar to Vista and A-Vista, definitely much better than the result that we have obtained with the same engine, the same solver, but without adding regularization. And you can see that the residual now is slightly will be slightly higher. The difference between the red and the black curve will be slightly more than the green and the black curve. And that's because we are asking to add some prior, and by adding some prior, we are saying we accept not to feed the full data. So once again, let's make some comparison in terms of convergence. And it turns out that if we're very careful with this exponential decay, our solver is not that worse than the ISTA algorithm. So if the developers or the inventors of Vista in 2011 did not invent Vista, by now you could probably say that you can solve this problem with ISTA or with just a automatic differentiation gradient with L1, and you get the same results. But luckily for us, Vista was invented, and I would say this is the preferred choice, at least my preferred choice for a problem like this one. Let's now move to a second example. This is a bit more exciting. It's taken the field of deep learning by storm a few years ago. And the idea is very fascinating. Everyone said for a long time, you need to train these neural networks with a lot of training samples. Eventually, they will learn what you're asking to learn. And then some guys came up and they said, we don't need that. We just need the problem, classical inverse problem. And we can just, instead of inverting for the model vector, we can invert for the weights of a network that is completely initialized at random. And we feed the network with some white noise. And the network will magically find out how to basically give you a solution that matches the data. Unfortunately, this magic does not always work. It works when the network or the network that you choose, for example, a convolutional neural network, will give you a solution that belongs to the space of solutions that a network can span, and ideally will give you the solution that matches the data best. But we will see in a minute that with convolutional neural networks, you cannot expect a sparse solution because convolutional neural networks are likely to give you a smooth solution. So most often than not, they have to start adding a second and a third and a fourth regularization term. And what we are doing here, we are adding a second term that simply says, we also want the output of the network, which now means the solution in our original model space, to be sparse. So what do we do? Instead of solving the problem straight from this vector x, we're going to create a network. In this case, we're going to create a UNet because it's been shown to be sort of the most powerful type of network for this type of approach. And then instead of solving directly for x, we will solve for these network weights. So how does it work? Well, first of all, unfortunately, I have to redefine the problem because in a certain way, neural networks are a bit inflexible when it comes to the size of the input data. If you have a size of 63, as we made purposely for the other example, when you try to do, for example, or design a UNet that has some downsamplings of 2 or of 3, eventually at some point that number will not be divisible by 2 and you will not be able basically to go deeper and deeper. So that's why most of the time you always make your images or your signal powers of 2. So we can make it 64. But that's basically adding 1 0 at the end. So it won't change very much the story here. But for this, we have to recreate the full pipeline. We create the PyLops operator and recreate the data and put it to torch. And now here is the magic. So compared to before, we are making two main changes. So the first one, we create a network that in this case is a 1D UNet. So UNet acting on 1D signals. The first layer will have 32 hidden channels, and then we are stepping down twice before going up twice in the decoder part. We also choose a different optimizer. Now, as I said before, Adam is not good for everything, but it's definitely good to optimize weights of neural networks. So we're going to leverage Adam. We also take away the scheduler. It's not that needed here. And then we have to create this random vector, the noise vector, and we'll do it using torch around then. And then we simply want to solve our problem exactly as before. So we're going to create our data vector. We're going to create the data term loss, the L1 loss, and sum them. The main difference happens here because instead of straight passing the vector that we want to optimize for into our PyLops convolution operator, what we instead are doing, we are first passing the noise into the network. We are getting out now a vector in the reflectivity or model space. Then we pass it to the PyLops operator. And now it becomes even more clear that you cannot just mix and match PyLops operators with very simple PyTorch native operations like mean or sum, but you can actually mix and match it with very complex neural networks, so very complex torch modules or any type of torch module. So anything that we did before will be the same. We're just gonna create the loss, apply the backward, and then step on the optimizer and keep track of some of the iterations. We will see. It's gonna come. The problem is gonna be slower because now we are not going through just a very fast modeling operator, which is a 1D convolution, where we have to go through all the time a network, as well as we have to go all the time backward to update the weights of the network. But as you will see when this is finished, the results that we get are actually very nice. So we are comparing now the data term loss and the L1 loss. You see how they go down end in end. And this is the solution that we obtain. So this solution is basically taking the finalized network that we have optimized for and simply, let me see. Yes, so we are simply taking the very last solution that we are getting up here. So this X DIP, and then displaying this X DIP alongside the X. So what is the conclusion here before we move on to the very final example? The network has finalized its training, so we can show the results. Well, the conclusion here is that deep image priority is nice, but for this specific problem, as for many other problems, it is very or terribly slow, I would say. So what we show here is the error norm as function of iterations for the solvers that we have used before and the two new solvers. And you can clearly see that perhaps the automatic differentiation with L1, we could have stopped much earlier. But for the deep image prior, if we just zoom in the first 1,000 iterations, you will clearly see that we are not there yet. We're getting there about 4,000 iterations. So one of the conclusions here is that there is not a unique solver that can be the best for every problem. Deep image prior is shown to be very successful for a variety of problems, but not for all. And finally, what about a fully data-driven approach? I just wanted to show it once again to remark a few things on the PyLops side, definitely not too many here, and more along the side of which tool should you choose for which problem. As I said already, there is no free lunch. Not one tool can solve any problem and be the best at any problem. So what we do here, we're just doing very standard deep learning. We assume that we have access to many reflectivities and many data. So PyLops comes in only in the sense of creating the training data for us. And now we reverse the problem. We are not feeding the network with this noise vector. We feed the network, which will be actually the identical architecture as the one we had before. We feed the network with the data for all the possible samples that we have in our training set, and we try to predict the model. And of course, we know, sorry for the typo, this should have been R. Of course, we know R, so we can set up a loss that basically tries to find the network weights that minimize the error between the predicted R and the true R. And again, we can use any norm, L1, L2, or any other norm that you fancy. So how does this work? Well, as I said, we create the training data. I made this fairly simple routine that is provided in the repository. It just takes a number of parameters, for example, how many spikes you want to have, or what's the minimum and maximum number of spikes you want to have, and then randomly samples one number, and it does the same, for example, for the minimum and maximum amplitude. So eventually, we're going to create fairly small number of training samples, just 2 to the power of 8. But for such a simple problem, they're going to be enough. And we are showing just one. So notice that the one I'm showing by chance has only one spike, but you're going to have a large variety, as we will see in a minute. So what we need to do, classical approach in Torch, you move everything to Torch. If you didn't want to create the data natively in Torch, as we, of course, don't want to rewrite code if we have access to code that we trust. We put it into a tensor data set, both for the train and test, and then we create a data loader, which has a certain batch size. We also create our UNet, and then all we're gonna do is a classical training, neural network training approach. We create a loss, which is, in our case, the MSE loss, so the L2 norm. We use, again, our favorite Adam optimizer. And then this is how I generally tend to set up my network training. I have a for loop over the epochs, then I have a routine for the training, one for the evaluation, and then eventually I do some storing and bookkeeping of things I want to display eventually, and do some printing to see how things are going. Inside the evaluation routine, I'm actually asking to plot the current solution every 25 epochs. So I see what's happening under the hood. And we see here, the black is a bunch of reflectivities on top of each other, and the red is a bunch of predicted reflectivities. Really bad at the start, not surprising. But with time, the network realizes that we want to have sparse solutions, very few spikes. And it starts to spiking up more. Epoch 50. And now soon, I think we're going to do 100. So we are halfway through. It gets even better. 75. Even better. We actually plot only 2 terms, so the loss is 0, but eventually, of course, it's not 0. And this is what it looks like, a kind of textbook train test, or validation, if you like to call it. We are not doing any hyperparameter tuning, so test and validation is the same thing here. And you see that there is definitely no overfitting. Actually, the test is slightly better at the end. And we are quite confident that this is going to give us a good result. So we're going to just take a few training samples, a few test samples, pass them through the network that has been trained, and let's see what we get. Again, very good results. We see that definitely the network is struggling with those very small amplitudes. Also, is struggling a bit more when you have things that are close to each other, what in geophysics we call tuning effects or events in tuning. Not surprising, I would say. But now is the moment of truth. What if we feed the original X vector, the original Y vector, the original data that we have created, as well as the data with noise? And that will be the most important thing to look at. What if the data has noise and we are not being able to create a training data with noise because we didn't really know much about what the data was going to look like? And this is the result that we obtained. So the purple is for the noise-free data. Very nice. I would say comparable to all the results that we have produced so far. And the blue is with noise. So this shows that with deep learning, you really need to have quite a lot of prior information. We have seen that for most of the algorithms that we have used up until now, our prior information is only limited to the fact that we really need to know, or we want to know, that the solution should be sparse. And that's why we design all our cost functions to enforce that. But we never really needed to know much about the noise. We just had one instance of data, we fed it through the solver, and the solver, with some stabilization, will give us a good solution. So here, in a way, it shows us that for problems where you have a physical operator, using deep learning and just completely forgetting about the physics could be a dangerous route. I'll leave it like this, because in my group, we are doing a lot of work in this direction, trying to combine neural networks with physics, in the sense that we are solving classical inverse problems and getting the network to help us for some of the tasks. So if you're interested, I think you can, in the next few months and years, hear more from us on more exciting and advanced topics. But for today, I hope you enjoyed the fact that we have been able to take a problem that has been studied from the 60s, 70s in geophysics, started from what has been used in the past, frequency domain, shown that if you do it in the time domain, you can actually get better results because you have way more flexibility, especially if you start relying on solvers that were developed in the last 10, 15 years by the applied math community, like the various proximal solvers that Nick presented. We have also shown that if you're good and careful, you can try to leverage some of the deep learning optimizers and the sort of deep learning new ideas like deep image prior. But again, you need to know that not every problem will be the best suited problem for these type of approaches. And as a sort of rule of thumb, if your problem has a modeling operator that you kind of know, throwing that modeling operator will put you in a very difficult situation to be able to beat sort of any other algorithm and knows that modeling operator. So the conclusion is there is always room for research, because there is no one algorithm that can solve any problem and be the best at any problem. So even if you find an amazing algorithm tomorrow, be sure that in 1 year or two, you may find another amazing algorithm that maybe is not that good for one problem, but it will be better for another one. So there will be time for every one of you, no matter how young you are, to make a contribution in optimization. And with this, I will leave it to Carlos. Or maybe, Carlos, we want to take a few minutes break since we ended up a bit early.
Hi, everyone. I don't know. It's up to you guys. I can keep going.
Maybe we keep going.
Yeah.
And people
All right.
they can always post in YouTube.
Yeah, exactly. And this is going to be up later, so I think it's better if we just get started. Okay. Hi, everyone. And my name is Carlos Costa. I'm one of the developers of PyLops. And very, very nice presentation by Nick and Matteo. And they really showed a lot of the power that PyLops has solving these problems. And they used a very simple operator, which is the convolution operator. However, PyLops has a lot of many other different operators, right? So it has derivatives, and it has smoothing, and it has radon transforms, and all sorts of operators that are useful, particularly in the geophysics community, but in other communities as well. And today, what I want to talk about is, okay, so what do you do if you don't really have these operators available, right? So what if you're solving a problem that you are, let's say, one of the first ones to want to tackle, or the operator isn't in the library yet, and you want to be able to generate that. So I'm going to talk a little bit about how I would go through the process of creating an operator and packaging it in PyLops. And I want to talk about that from a point of view of PyLops version 2, right? So in PyLops version 2, we're really trying to make it easier, even easier for either the user or the developer to go from 0 to hero with their new operators. So to tackle one of the problems that we're going to try to tackle in this tutorial is the very simple problem of shifting a vector, right? So let me
Carlos,
scroll down here.
Are you sharing your screen?
I should be, I guess. Okay, here we go. Sorry about that. 1 second. There you go.
Yes. Now we see.
All right. Thank you. Yeah, thanks. Okay, so yeah, so we're going to try to implement a very simple operator. That's the shift operator. And we have a few restrictions, right? For this problem, we're going to look into a few restrictions. So first of all, we want to be able to shift our vector a fractional number of steps. So normally, if you want to shift a vector that it has, integer positions, usually you shift a few samples. But what we want to do is we want to be able to shift an even fractional number of samples. So this is going to be one of the restrictions that we're going to be looking into. Second restriction is we want to be able to handle multidimensional arrays. So we're going to want to shift those arrays along a certain axis. And just in terms of setting the ground rules, the shift to the right is going to be a positive shift. The shift to the left is going to be a negative shift. And finally, our shift is not going to be circular, which means that when we shift to the right, the samples that are at the end, they just get dropped off, and they don't appear in the beginning of the array. They actually just get dropped off. And in the beginning of the array, we need to put something in there. So we're going to be putting zeros. Okay, so these are the restrictions, right? And I want to bring your attention to the fact that PyLops does have a shift, right? And and it's a very fancy shift operator that Matteo wrote, and it's in the Fourier domain, and it's very, very nice, and it works for fractional numbers. But for our purposes, it's not circular, and we want to create one which is circular, which is not circular, right? So his is circular. We want to create one that's not circular, just for the point of the exercise. And we also want to bring attention to those of you that are NumPy users. NumPy has the roll function, but not only it does not support fractional shifts, but it is also circular. So these options, we're not going to use these options. We're going to be creating our own, just to go through the exercise of actually writing your own function. And so before we get started, I just want to bring your attention that everything in this notebook is going to be requiring the development version of PyLops. Hopefully this will be in the master very soon as the 2.0. But for now, it's in the dev branch. So if you want to give that a go, be certain that you're probably going to find bugs. So please give us a shout if you do. But at least I hope that I don't run into any of them during this presentation. All right, so we're just going to be loading a bunch of libraries here. We're going to be loading Numba, which is basically a just-in-time compiler for for Python code that makes Python go fast, basically. We're going to be using NumPy, rely on NumPy a lot, and we're going to be bringing in PyLops. And if we have time, we're going to look into using CuPy, so basically using CUDA arrays in Python to make this go really fast. So let's just have a brief look at how we actually want our operator to work. So for an integer shift, so for a whole sample shift, the way that we're going to start this is we're going to take an array, right? And we're going to do two things. So first, we're going to crop it. The last two samples, let's say in this case, our shift of 2 is we're going to throw those samples away. And then we're going to pad the beginning with zeros, right? So there are many, many different ways of doing this, and please feel free to write your own. But just for the purposes of this exercise, what we're going to do is we're going to be concatenating. This should be running. Maybe I didn't. Already running into problems here. I did not activate my. Just a second. All right, so this should be working now, hopefully. Forgot to activate my environment, so that's a classic. All right, so I don't have a GPU in this computer, but that's okay. All right, so what we're going to do is we're going to just concatenate, right? Zeros. So basically, we're going to create a zeros of the size of the shift. And then we are going to crop, right? So we're going to just get rid of all the samples that are, on the end of the array. So this should work. This should work. So let's have a look. All right. So we have the original array, and here we're shifting by 3. So that looks pretty good. Now let's try a negative shift. So negative shift, and we're going to be concatenating, but now instead of putting the zeros at the end, we want to put the zeros in the beginning. Sorry, instead of putting the zeros in the beginning, we want to put the zeros in the end. Instead of cropping the end, we're going to crop the beginning. Right. So here, remembering that the shift is negative, we need to put a minus, and then just take everything after that. And then we just need to pad that with zeros, right? So again, remembering that the shift is negative, we put a minus here. So so this should look pretty good. I hope it looks good. All right, there we go. So 3 samples taken at the end. Put 2 zeros, 3 zeros at the end, and then we just crop whatever is in the beginning. So this is looking like a pretty good integer shift. Sorry about that. Oops. I don't know what's going on here. Okay, some issue there or other. But yeah, so I'm just gonna copy paste a bunch of code here, just so we can actually make sure that everything is actually making sense. So in reality, what we notice is that if we try a bigger shift, right, so a shift of 12 or a shift of minus 12, we actually run afoul of our array, and we actually create an array that is a little bit too big, right? So this code here isn't perfect, so we need to improve it a little bit. And the way that we're going to do that is we're just going to basically clip our shift to be in between the length of the array or minus the length of the array. And if we do that, then our shift should work just fine, right? And in fact, so here's a function, and I'm just going to test it out for all the shifts that I tried before. And this looks good, right? So now we fixed this little issue. And again, there are many different ways of doing this. This is probably not the best one, but it's just for us to kind of get an idea of how I would start building a linear operator. So we have our 1D shift, and this is only integers, right? So we want to actually make this work for any kind of ND array, right? And this is something that we, in a lot of different operators in PyLops, we need to do. So I want to go through some of the motions that we would do to actually achieve to apply something that would only works on 1D arrays to something that works on ND arrays on any specific axis that you choose. All right. So let's have a look here at a 3D array. So here we have a 3D array that is size 2, 3, 9. And what we want to do is we want to shift along the last axis, right? And so for us to do that, we're gonna do some of the motions that we normally would do in a lot of PyLops operators. So we're going to take the swap axis function, right? And then we're going to take our 3D array, and we're going to put the axis of interest in the last coordinate, right? So in this case, the axis is already -1, but if we put like, I don't know, a 0 here or a 1 here, this should also work. I'm going to leave it as -1 here, but one of the interesting things of swap axis is that swap axis returns a view, which means that it doesn't actually copy any data, it doesn't actually transpose any data. All it does is it changes the header through which NumPy accesses the memory in this array. So it's essentially a free function, and we don't need to worry about this. We can do this very, very fast. Now, after we have basically switched our axis to the last one, we know that we can always index this axis through the last axis, right? So now what we are going to do is we're going to crop. We need to crop and we need to pad. So we're going to start with a crop, and we're going to do that by just taking this temporary vector that we created, and I'm going to select the last axis. And the way that I'm going to do that, I'm going to use the ellipsis operator that NumPy supports. And here we go. So basically, the way that this works is basically this ellipsis operator here. What it does is it selects all of the dimensions that are before the last axis. So if we wanted to do, for example, in the 3D array, this would be equivalent to this. In a 2D array would be equivalent to this. In a 1D array, it would be equivalent to this. So this is just kind of like a generic operator that we can use, and we can always index these arrays. All right. So now after we cropped, we need to also pad. And the way that we're going to do that is we're going to create a padding of the shape that we require. So first, we're going to just copy the 3D array shape, right? And in fact, we're going to create the 3D array temp shape. So basically, this is the one that we've swapped the axis. And then we're going to change the last element, right? The last axis, which is the axis that we actually want to shift. We're going to just make that the size of shift. So the absolute value of shift. So if it's a positive, it's going to be a positive. If it's a negative, it'll also be positive. And so for us to create the pad, all we now need to do is just create a zeros the size of pad shape. Cool. So now we have the crop and we have the pad. All we need to do is concatenate them. So let's just concatenate them. There we go. And axis equals -1. All right, cool. So this should be working. We should be able to get our shift going. Here we go. We're putting 4 shifts in the beginning of the array, right? But now the one thing that we need to take care of is the fact that this guy has the axis of shift in the last axis. And for us to actually make sure that it is in the correct axis, we need to swap back the axis. So we're just going to give shifted and then axis and then -1. So this will just shift back to the axis that we actually want to do. In this case, it doesn't do anything because the axis we're shifting is the last one. But if we were to maybe change this to 0, this will work out, right? So since the shape of this array is 2, if we get all zeros, if we want to shift on the last axis, and maybe we just want to shift 1, we get a shift on this second axis here. So this is looking pretty good. We're just going to wrap this into a function, right? And I'm going to change a little bit the code, but basically, yeah, if the shift is too big, I'm just going to return zeros. There's no point computing pads and so on and concatenates. And then swap the axes, create the pad it in different ways, and then swap the axes back. So pretty straightforward. And now what we have is we have a function which does an integer shift, right? Does an integer shift, and it works for positive, negative shifts. So what we were looking for, and it's not circular, but the only thing it's missing is it's not fractional. And the way that we're going to create this fractional shift is we're going to shift. So let's say we want to shift by 0.5, right? So shifting by 0.5 is kind of like halfway shifted between 0, so no shift at all, and shifting by 1 sample. So the way that we're going to create like a 0.5 shift is we're going to take the shift by the floor and the shift by the seal, so the floor plus 1, and then we're just going to divide that by 2 in the case of 0.5. Now, in the case of other numbers, right, all we need to do is make sure that we put a little bit more weight to the sample that it's closest to. So if the shift is at, 0.9, so we want to shift it closer to 1. If the shift is at like 0.1, you want to put a little bit more weight closer to the floor. So this is just a very simple linear interpolation, right? And we're going to leverage that. We're going to be leveraging that for our linear shift and a linear shift that works in ND arrays. So that's let's try that out. And that again looks pretty good. So just printing X here, 1 through 9, and then a shift of 2.1. Here we have the 2 zeros, but then the 1 gets a little bit, let's say, penalized, right? Because it's we're not shifting exactly at 2. A shift of 8 takes you all the way almost to the end of the array and leaves 1 sample, so that's working fine. And a shift of 9, which is the bottom one here, zeros everything. But a shift between 8 and 9 doesn't zero everything and also doesn't keep the last sample properly, right? It puts a little bit of a weight there. So this again is looking fine. And this is really the process that I would go through to actually create a function that I'm going to rely on to build my linear operator. The whole point of the linear operator is to wrap these operations that are linear into something that you can use for matrix multiplication, for solvers, and Matteo and Nick showed a lot of how they can be leveraged. They can then be converted into torch operators and so on. So basically, if you're just able to wrap a function into a linear operator, it gives you access to a lot of the different tools in the ecosystem. And so this is really, let's say, the starting with the linear operator. The meat of the tutorial is how do you actually take a function, in this case, this shift ending linear, and make it into an actual linear operator. So the way that we're going to do that is we're going to create a linear shift class, and that's going to inherit from the PyLops linear operator class. And we need to basically create, for starters, we need to create two functions. So these two functions are going to be initialization, right? So we can actually set all the parameters. And then we're going to create matvec, which is going to handle all of the multiplications by vectors, right? And then after we have a matvec, then we're going to be able to do any sort of like forward multiplication. So let's start here with the linear shift. So we have a couple of parameters that we're given. So the shift, I'm just going to store that. We have the axis, and we're just going to store that. Okay. And what else do we have? We have the dimensions, and we have dtype, and so on. So dimensions and dtype and the name in this case, this is also a 2.0 feature. They are all part of attributes that the PyLops linear operator have. So instead of just setting them directly, which I mean you can do, but instead of setting them directly, what we're going to do is we're just going to pass all that. We're just going to offload all of those creations settings into the super init class. So have a look at the super init if you're a developer and you want to see what this actually does. But basically, what you need to do is you need to create the shape and you need to create the name and the dtype. The only ones that are really required are dtype and shape. And instead of shape, what we can also supply, and this is again also a new feature of version 2, is you can supply dims, which is basically the dimension of the input array. So in the previous case, this was like 2, 3, and 9. And we are also going to give it the dimensions of the output array, so the data. In this case, because it's the same size, I'm just going to give it dims. And then finally, name equals name. So anytime you are trying to assign a dtype, dims, dimsd, name, shape, and these other kind of like class attributes that linear operator has, just use the super, because this will register a bunch of other things. You're not forced to, but it's just like good practice to do that. Now, after we have our init, so this is what gets called when our operator gets initialized, we need to implement the function which actually does the multiplication. Right? So in this case, what we're going to do is we're going to take x, which is going to be a 1D array, right? So this is usually how it was done in 2.0. So you get an array that is always flat, right? And we're going to reshape it into the size that we actually need. And that's why one of the reasons why we need to keep dims around. Now we reshaped it. Now we're going to apply our function. So that's our function here. Just pass x. The shift is going to be self.shift. And again, that's why we need to save it. And finally, axis going to be self.axis. All right. So this is, we're almost done here. The only thing that we're missing is we need to do a y.revel. matvec, because of the way that the compatibility with SciPy and other libraries work, matvec always is going to take a 1D array. No matter what you're doing, matvec should always be taking a 1D array. And then internally, you would have to reshape it. This is kind of the 2.1 version. I'm going to show you how we can simplify this a little bit in the 2.0 version, but basically, matvec should be multiplying by a vector, and we need to make sure that that's the right thing to do. All right, so I'll create this operator, and we're going to just initialize it with the 0.5 shift, and we're going to describe it, right? So describe is a new feature of PyLops 2, and you can like combine any sort of like different operators here. So basically, we'll be able to describe things very well, right? There's a little bug here, but yeah. So basically, now we have this operator, and we can actually make it run, right? So This is, again, the 1.0 version. I'm going to show you guys how we can simplify this in 2.0. But just to take it for a spin, we're going to multiply this operator by this 3D vector that's been flattened, and then we're going to reshape whatever comes out of it. And this actually makes sense, right? This is what we were expecting to get. So instead of shifting 1 and instead of shifting 0, it kind of shifts halfway in between. So that looks good. Now, I want to show you guys what happens if you try to do the transpose of the shift. And this is going to be a long error, so I just put a little try except here. But basically what happens is that it fails with an attribute error because the transpose doesn't exist yet, right? So where did it go? Well, we didn't create it. And for us to create it, we need to fill out this other function called rmatvec, and this is just like a standard function that we inherited basically from SciPy and NumPy and so on, and we need to overload that as well. So I'm going to go through how it will do this. In this case, what is the actual adjoint of our shift? Lucky for us, this is just a negative shift, a shift in the negative dimension, in the negative direction. So what we're going to do is we're going to take the same kind of boilerplate steps. We're going to reshape, but now we need to make sure that it's dims, the dims of the data. In this case, the same, but it's just good practice to write the dims properly. And now we're going to shift, right? But instead of shifting positively, we're going to shift negatively, right? So here's just a negative in the shift. And finally, whatever comes out of this, we are going to make it into a 1D vector. All right, let's see if that works. Hey, that worked, right? So that's actually doing the right thing. And if you see here, I took the shifted vector that I created before and I applied the transpose. And then I reshaped it. And you see that in some of these elements, it did, let's say, what we were expecting, right? It was shifted to, let's say this was 0.5, and then it was shifted back to 1. So this is doing the correct thing. The last sample, on the other hand, because we lost some information, we shifted kind of half of the last sample off. When we go back, when we do the transpose doesn't actually recover what we had before. It's not the inverse, right? But just to make sure that what we're doing is correct, we need to go through the dot test. And the dot test is just ensures that the operations for matvec and rmatvec are actually transposes of each other. So just to give an example of what that means, before I run it, I'm going to create something that does not actually respect the dot test. So here in rmatvec, I'm going to put a bug here. So instead of just shifting, we actually put 2 times here, just as an example, right? You see that, okay, this doesn't look right anymore. And if we run the dot test, it's going to complain. It's going to say, look, whatever it calculated with the transpose is not what it calculated with the forward, right? So this uses the adjoint identity to verify that these 2 things are the same. And it says it's not the same. So you have some sort of bug there that you need to take care of. We're just going to get rid of that. And let's hope it passes. There you go. Dot test passed, which means that the forward and the adjoint, they're true mathematical forward and adjoints of each other up to the precision that is used. So if you want to change that, you can maybe do, insert on. There we go. You can do 1 minus 9 or something. And there we go. So that still works. Let's see, down to like some higher numerical precision. So that still works. Of course, if you go, I don't know if this is going to work, but if you go to some like insane numerical precision, that's going to fail, right? Even though the numbers look very, very similar, because the floats don't support this range. So of course, it's not going to work very well. All right. So now that we have our operator working, we're going to describe it. Cool. Okay. And now what we're going to show is how this actually looks like when we shift back in the adjoint, right? And so to do that, we're just going to take our linear operator. Sorry, we're just going to take our linear operator, and we're going to apply it twice. So there we go. So apply the transpose, apply the operator, and apply this to our X3D. And then after everything, we reshape. Let's say something. Okay. And we see that it says, look, the shifted back isn't exactly the same as the initial. And this is obviously expected, right? This is what we saw previously. The shifted back isn't really what we were expecting. I mean, it's not the inverse, right? So it's not going to be exact in these locations. So what is one of the things that PyLops offers is PyLops offers these solvers as both Nick and Matteo show. And I'm just going to show one that overloads a division operator. So so here I have my linear operator, and I'm just going to take the shifted vector that we had before. Oops, the shifted vector that we had before. And I'm just going to divide the operator by that, right? So this is something that will not work if you are using a SciPy or a NumPy operator or a matrix. This is only working because the linear operator that we defined, that we created, it embeds, right, overloads the division class, and the division method. And the division method will take whatever is on the right-hand side, and it'll solve a system with this right-hand side. And so this should then give us a vector, which we'll reshape to be the same shape of the data. All right. So this looks pretty good. Actually, sorry, there's a bit of a bug here. So this looks pretty good. Should be like that. Well, I don't know how to do backspaces. Maybe this. I don't know. Backslash. Some latex. No, that's okay. You guys get it. Div. So basically what it's saying is, look, if you use the solver to actually invert the system, you get something which actually looks pretty close to the true shift. But this is a little troubling because, you know, we lost some information there. How did this get it back? Well, if we actually try a harder problem, I'm not going to code all this from scratch, but if we try a little bit of a harder problem where we take our linear shift and are just creating one that shifts a lot by almost 6 samples, and then we take some noisy data that is sampled away from 0, so we don't bias our solution towards the 0. And we just do the same thing, shift it, and then shift it back and compare it with the opposite. What you see, oh, here you go, that's the backslash. And what we will see here is that in black, we have the original data. In blue, we have the adjoint, right? So we have the shift and shift back. And then finally, the orange dashed line shows the inversion. So we see that the inversion actually matches our data very well in most places, but in the places that it loses information, it just sets that to 0. And in this case, the adjoint also does that, but it might not, right? And in fact, another interesting part of the adjoint is that because this shift is actually quite big, right, in this for the size of the array, it actually impacts all the data that is inside of this of the region of the shift. So the inverse will actually bring where you have information, actually bring it back to match the array, but the adjoint will not. So it's important to make sure that when you're solving these systems, you're just not assuming that the adjoint will give you the inverse, right? Okay, cool. So just a final comparison here. I wanted to show how this compares to a NumPy least square solution. So in practice, you wouldn't really have access to this matrix here. This is a matrix that's created from our linear operator. In practice, you wouldn't have this, right? Because this actually is a very, very large, usually it would be a very large matrix, and you don't have access to this. But because we do in this case, I want to compare and make sure that it's actually matching the least square solution that we obtained. So let's just have a look at that. Again, this looks pretty good. Black is our signal, and now just have a look at the gray and the orange that are superimposed, I guess, and they look very, very, very similar, almost numerically the same. So our matrix inversion, our dense inversion, is actually giving pretty much the same solution as our least squares. However, the least squares solution, we didn't really need to solve invert a matrix numerically or anything like that. We just threw it in our solver, and we never actually had to compute this matrix in the first place. All right, cool. So moving on. Now, you saw a lot of our code has this reshape Ravel kind of pattern, both for the user who is applying the vectors, but also for the developer who is creating the linear operator. And I want to show you what happens if we just take this linear operator here. And before, if we wanted to multiply this by the 3D vector, we'd have to do something like this, right? And then our y shape would be a 1D vector. But now, if we actually do this, we are actually taking an ND array, and we're just using the same multiplication. Remember, this is the same code that we wrote before. Right? So nothing changed in the operator. However, PyLops now comes with the capability of handling ND arrays as long as, I'm just going to create a little, as long as the operator here has the compatible dimensions. So because this and this are the same, the linear operator is able to figure out that this vector here is not actually a matrix or anything like that, or something that's the wrong shape. It's actually able to figure out that this is a vector, but it's just been reshaped, right? And so because it knows that, it also knows that the output should have dims_d, so the dimensions of the data. And so if it takes a flattened array, it knows that it needs to output a flattened array, so this is backwards compatible. Most of it is backwards compatible. And so if it takes an array that is flat, it'll know that. And if it takes an array that isn't, it'll also know that. So this actually works pretty well. And you don't have to be writing this like reshape Ravel all the time. And what's even cooler is that this will propagate, right, in a lot of different operators. And you basically never have to think about doing reshape ever again. At least that's my hope. All right, so then we have X like 3D, for example. Again, figure it out because it knows that this guy was not flat. Therefore, the output of this was not flat. Therefore, the output of the entire thing was also not flat. Cool. So we can even do this for these quote-unquote ND array matrices. So here we have, here we're creating a new, let's say, quote-unquote matrix that is the shape of our array, so 2, 3, 9, but has two of those. So because we're concatenating them along this last dimension here. So if we actually write this, if we actually try to multiply them, this works, and this works very well because it knows that these operators here, they're looking for something which will look like this, right? So dims that has the shape, sorry, dims, comma, and then just a number of dimensions here. So if it sees something that looks like this, right? So the dimensions, and then so this would be something like dims 1 all the way to dims. And if you find something like this in this shape, it knows that this is kind of a matrix looking object, but for an ND array. And it works just fine. All right, cool. So what this means now is that our operator that we never changed works for ND arrays. But what happens if we have this sort of pattern, which happens all the time, which is we need to take a 1D array. So the implementation doesn't actually change how the matvet works. It only changes how it's handled. So this X should still be something that is flat. So you still need to do the X reshape and the Y Ravel all the time. However, what I'm going to show you is that we developed some decorators that allows us to get rid of all this boilerplate to focus only on using the X as you would expect it to be, right? In the shape or in the dimensions that you'd expect it to be. Not only it's able to simplify this code that is very, very common in our library, but also code that looks kind of like this, right? So where you have a reshape and a swap axis, and then a kernel which operates on the reshape with the last axis of interest, and then swaps back. And there's actually a bug here. I mean, this isn't code, but it's just good to make sure that this is right. And then it swaps back, and then it revels. So these are two very common code patterns that are just everywhere along our library, and we want to simplify that to make sure the user doesn't really have to worry too much about these reshapes. And we caught quite a few bugs in our libraries because maybe we forgot the swap axis, maybe we didn't revel at the end, and things like that. So I wanted to make sure that this never happened again. Right? Now, if we just have a look at how they would look, these two codes, instead of doing reshape revel, you can just put the decorator reshaped on top, and then you can assume that the X is already been reshaped and the Y as it comes out will already be reveled. And if we also want to swap axis, we just put a swap axis equal true. It'll take the self.axis and it'll just use that to put it in the end. So the difference from these two is the axis of interest is always going to be -1. Okay, so we're reaching kind of the end of our tutorial here, and I just wanted to show how we would put all of this together. And I know there's probably a lot to take in right now, but I just wanted to show how we could put all of this together to make a pretty cool linear operator that works not only for NumPy, but using Numba, which is a just-in-time compiler, and also using CuPy, which allows us to use GPU arrays for CUDA video cards. So the way that we're going to do this is the init is going to look quite similar in the beginning, right? So we have the shift, we have the axis, right? But now we are going to have an engine that is going to be Numba if the user chose Numba and you actually have Numba available, right? If you don't have Numba available, you're just going to fall back to NumPy. And then we're just going to register that. So the D type, this can probably just go in here, for example. So we're just going to register the D type, the dims, and the dims D, right, which is the same, and the name. So this is the same as we would do in the previous one, but now we want to be able to use all these different frameworks for computation. So what we're going to do is we're going to set the engine, and then we're going to call this method that's called register shift ND linear. So this method here is going to register in our class the different methods that we're going to call depending on the different engines. So let's have a look at how this looks like. Now I re-implemented the shift ND and the shift linear so that they would work for Numba, CuPy, and NumPy all in one function. But if you don't either know how to do this or it's not possible, a lot of the times it's not possible for a certain problem because neither Numba nor CuPy support the entirety of NumPy. So if you don't know or want or even can do this, you can just register different functions. But for the purposes of this exercise, what I did is I created two auxiliary functions. One which will be called by our matvec, as you can see here, and the other one which is auxiliary. And then we're going to, for the Numba engine, we're going to compile that. So this is just equivalent to maybe putting like JIT here, as people who are familiar with Numba would do. However, because we also want this to be available for NumPy, I'm only going to JIT this function if the engine is Numba. Okay, and we need to JIT all the functions that are used by Numba. So if the engine is Numba, we're going to JIT it and then store it in this method here called shift ND linear. So then what we can do is we can just call our matvec, and now we're going to put this decorator and swap axis. And now you could have a look at the code here for these two functions and see that they always work on the last axis. So it really simplifies the coding if you can just assume that, right? And just a heads up as well for people who are coding this and want to get the best performance out of your code. If you're iterating over your last index and you're and your vector was created with your last index already there, this should give you the fastest speed up, the fastest way of iterating. So try to do that. Try to always make sure that you're applying things on the last axis. All right. So after we register this function and create the same thing for the matvec, I'm just going to run this and take it for a spin. So it will be a little slower on the first run because Numba is compiling the function and then running it. But then on the second run, this should go pretty fast, right? And then you can actually do I don't know, time it or something to make sure that you're actually getting a pretty fast function, right? So it's 900 microseconds. So really not that bad. Now, I'm going to switch very quickly here. I don't know if I'm going to have time, but I want to switch to, since I don't have a GPU on my computer, I'm going to switch to, don't restart. A second. I'm just going to switch this to, oops, I think my computer could have, oh, here we go. All right, so I'm just going to take us through, oops, cancel. I'm going to choose our runtime to actually have a GPU. And then I'm just going to run this. It's okay. Make sure that I install. Sorry, I'm sorry I have to do this right now, but the kernels dies if you don't play around with it. So this shouldn't take very long. But basically, I just want to show you that this, if you just plug in a CuPy array that has been moved to the GPU, this will still work using the NumPy engine because the functions that we created only basic call functions that the CuPy understands, right? So let's see if this worked. Okay, that looks good. We can just run through everything. No error on the CuPy, so that's all good. Just gonna run through everything really quickly. And right. So NumPy engine again takes a little bit in the beginning to get going because it's compiling. And then the GPU, again, using the NumPy engine, should hopefully work. Right. Maybe, I don't know why it's taking that long, but yeah, basically the code is almost exactly the same. While this is trying to figure it out, let's go back to the code here. And so some of the things that I changed, right? So I replaced the zeros because basically I didn't want anything that has NP in it because that's NumPy. But if you want to use like CuPy and you want to use NP, one of the things that you can do is you can just do this PyLops dot get device. Oh, sorry, it's not going here. But we have a utility function that allows you to choose either NP or CuPy based on where your array is stored. And then you could just like replace all your NPs with NCP, right? That will then be either NumPy or CuPy, and it should work, basically. I don't know why this is taking so long. Nope. But yeah, so I guess I will stop here and maybe try to run this in your own computer if you have a GPU. I have faced some other problems with Colab, but yeah, in general, it shouldn't be taking this long. All right, so that's it.
Very good. Thanks, Carlos. Really good to see what's been done and what to expect too with the next version here. Very exciting. Yeah, everyone. So that wraps up this session of Transform 2022. I want to thank Carlos, Nick, and Matteo for for their work on this. Very interesting to see what's going on. Again, just want to give a shout out to CurveNote for their support of the conference. We really appreciate that, and they have a lot of great documentation hosted on on Transform itself, and you can go and check them out. So with that, we'll turn this off. This tutorial will live forever on YouTube. But yeah, if you're looking for other things to do for Transform, we have a Birds of a Feather session coming up in a couple of hours. Tomorrow we have the annual general meeting and also some lightning talks, which are always exciting. So be sure to check in that if you're watching this live, and if you're in the future, then you can click on the YouTube link and see them all there. So with that, thanks everyone, and we'll hope to see you soon.
Thank you, Brandon. Thank you, everyone.
Thank you,
Thank you, everyone.
Great.